Hello everyone, and welcome to this presentation of the BrainDecode Toolbox. So what is BrainDecode? In a nutshell, if you just had to remember one thing from this whole presentation, it's an open source library that you can use to decode brain signals using deep learning models. And I will be talking about this toolbox because it's played a very central role for us when we developed the EEG Foundation Challenge. We used BrainDecode to create the whole data pipeline, and we also provided models from BrainDecode as a baseline for the participants of the competition. Before we dive in, my name is Pierre Getschel. I'm a PhD candidate at the Data-Driven Neurotechnology Lab in the Dandos Institute. My PhD focuses mostly on deep learning techniques for BCI decoding. I was particularly interested in transfer-learning questions, and now I am more focusing on self-supervised learning for building foundation models. I will be giving this presentation as one of the maintainers of BrainDecode because it's a library I use every day in my work. It's very useful to me. You have also a few links below. If after the presentation you still have some questions or you just want to reach out, feel free to get in touch. I'll be happy to answer any question. So as I mentioned, BrainDecode is a toolbox for decoding EEG signals and brain signals in general using deep learning models. And you may already wonder, why is such a toolbox even necessary? Well, the first thing is that EEG is a very specific data type. You need specific functions to preprocess this data, and you need specific functions also to load the files associated with this data type. On the other hand, you have deep learning. Deep learning, like there's a very clear trend at the moment showing that deep learning models are very promising or are already obtaining some good results, even state of the art sometimes. But deep learning is also known to be data hungry. So you need efficient pipelines to provide enough examples per second to these deep learning models such that they can be trained. Because you need to be able to handle very large amounts of data and very quickly. And so we have deep learning strategies, deep learning libraries, such as PyTorch. We have EEG libraries, such as MNE, but they were developed side by side, like in different contexts. So they were initially not meant to work together. And this is where BrainDecode comes in as a glue, basically, to make these different libraries communicate together, to have a smooth synergy and efficient data piping between those libraries. And so you see that BrainDecode comes on this diagram on the right side. BrainDecode is really in the middle, and we have three main interactions with external libraries. So you have on one side MNE that is used to load the data and preprocess the recordings. You have PyTorch, which is a deep learning library, and it's in PyTorch that we implement all the deep learning models. And finally, we have scikit-learn, which is a machine learning library. And we use scikit-learn to evaluate all of our models because all the PyTorch model can be wrapped into a scikit-learn estimator and fully compatible with the whole scikit-learn ecosystem. And so if you're already familiar with one of these libraries, you will feel at home in BrainDecode because we try to stick very closely to the conventions that are introduced in those three libraries. So you will feel at home, and it will be easier to understand BrainDecode if you already know one of these libraries. And so this brings us to our target audiences. BrainDecode is really meant for two main target audiences, either if you're a neuroscientist that want to start working with deep learning models. We will make that easier for you because you will have a collection of deep learning models available to you with just a few lines of code very easily. Or on the other side, if you are used to work with deep learning and want to start playing with neurophysiological data, BrainDecode will also make that easier for you, because you will have a lot of examples of how you can pre-process some EEG data, how you can load it into your model, etc. Okay, but concretely, what can you find in BrainDecode? So we have three main resources we provide for BrainDecode. The first one is a large collection of models that are ready to use. Then we have a large collection of data sets and all the preprocessing functions you may want to apply on EEG data. And finally, we have a rich collection of tutorials that cover many possible use cases you may encounter when you want to use deep learning with EEG data. And now I will walk you through these three components in the rest of my presentation. So first, the models. So in BrainDecode, we have a large collection of 46 models, all from recent publications. And all of these models, they are trying to solve the same problem, which is to decode the brain. So because of this assumption, we know that every model should receive an example X, which is a window of shape number of channels by number of time samples, and return a label Y. This is how decoding the brain is defined by Jeremy King. And thanks to this common assumption, we have, for all the models, standard arguments such as the number of channels, the number of time points, the sampling frequency. And all the models are able to receive the exact same argument with the same name. So we have a common framework, and you can just swap one model for another one. And you know that every model will have these exact same parameter names, and that you will be able to pass to the model the exact same window of EEG signal, and you will always get a label. And so you can, it's very easy then to benchmark different models or just to try a new model from a new publication. You don't have to update all of your code. It's all handled by BrainDecode thanks to the standardization. And finally, we also have a wrapper that takes a BrainDecode model, which is in PyTorch, and turns it into a scikit-learn estimator. This way, you are able to evaluate your model the same way you would evaluate any other machine learning pipeline. If you are very familiar with scikit-learn, that can be very convenient for you. So in the documentation, you can find the list of all the BrainDecode models. And so you see that for every model, you have the number of parameters this model has, sampling frequency that was originally used by the authors. You have mandatory hyperparameters. You can sort this model by number of parameters, like from smallest or from the largest. If you click on one of the models, you have the detailed card describing that model with sometimes a diagram explaining the architecture. You have all the parameters that are explained. These first 6 are all the mandatory parameters that you will find on every BrainDecode model. So the number of outputs, the number of channels, or like detailed information of the channels, the number of time points, the size of the window in seconds, and the sampling frequency. So they are not all mandatory in the sense that you don't have to provide them all. But let's say if you provide the number of time samples and the length of the window in seconds, then the sampling frequency will be automatically inferred. And this for every models. And at the end of this card, you have for every model the reference to the publication that initially introduced this model. And you see that you also have a categorization for all the models. So, for example, this model, you have a convolution and large language model and channel. And then if you look at the model categorization tab, you have a bit more details on like a basic introduction for every type of layers that you can find in the model. And so this work of creating a nice documentation and categorizing the models, adding these explanations, modularizing the models, all this was done by Bruno Arestimuna. So he's the main developer of BrainDecode, and a big reason for why the BrainDecode documentation looks so nice is because of Bruno. Then the data. So it's crucial for deep learning to have access to large amounts of data, and this is what we provide in BrainDecode. So first, natively in BrainDecode, you have some efficient data loaders for various paradigms, such as motor imagery, sleep recordings, or clinical data set, like, for example, the Temple University Hospital data set. And you have access to also every bits formatted data set. So I won't get into bits, but too much into details. But like the idea of bits is it stands for the brain imaging data structure. And it's a way to format your data. It's supposed to be the common way everyone should use to format their data sets when they want to share them. Because thanks to this common format, everyone is able to load any bits data set with the same functions. And so in BrainDecode, we support bits. And if you have a bits data set, you will be able to load it in BrainDecode. Then BrainDecode is also the base for EEG data sets. Again, I won't go too much into details because EEG has been mentioned already today in this workshop. But so through EEG you have access to an even larger collection of data sets. And finally, in BrainDecode, we also provide all the necessary methods and tools for preprocessing and saving your data. And finally, we have the tutorials of BrainDecode. So we have a rich collection of 27 tutorials that explain you how you can do many different things. So we try to be exhaustive in terms of possible use case scenario. And so, for example, we have an example of how you could use BrainDecode and interface it with scikit-learn, or how you could train a model on a bits dataset, or regarding the interface with MNE, or how you could do hyperparameter search. Later, I will zoom in on two tutorials. So one is how you can fine-tune a foundation model. So it's the last addition to our tutorial collection. But first, I will walk you through a very entry-level tutorial for new users. So in the documentation, you will find tutorials grouped by category. So we have 4 categories. The first one is regarding basic model building and training. Then you have tutorials explaining you how you can load and organize your data using BrainDecode. Then we have some advanced neural network training strategies. And finally, some real-world examples. And so if you click on a tutorial, you'll see that you have, it starts with the table of contents. So you can click on the section you want to go. And basically, you will have sections of text explaining some context and what is happening in the book. And then you have sections of code, and below this code, you have the output, like what happens when you execute this block of code. And if you go all the way to the end of the tutorial, you will find some links. So the first one is a link to download the notebook as a Jupyter notebook. The second one is to download the same example, but as a Python script this time. And finally, you can download it as a zip file. And so the way we recommend you to use this tutorial is first to find the tutorial that matches the most what you want to accomplish with BrainDecode. And then you start by downloading one of these examples, and you modify it to suit your use case. But before we dive in that, here are a few statistics about BrainDecode. So we're clearly the largest library for EEG decoding using deep learning. We have 30,000 downloads in the last month and 13,000 in the last 7 days. A lot of people are contributing on GitHub, like many stars, many forks. And BrainDecode is alive just because of its contributors. So if you are interested in contributing, you're very welcome. We have, we are always welcoming new contributors. So I will now walk you through 2 tutorials. In the first one, it's going to be a very simple and common use case in which you are a neuroscientist, you are already working with M&E, you have M&E epochs with your data, and you're interested in trying deep learning. So you start using BrainDecode. And in this tutorial, I'll just show you how you can train any BrainDecode model on your M&E epochs or evaluate a model on your M&E epochs. In the second tutorial, I will show you, it's a bit more advanced, I will show you how you can fine-tune a foundation model on data from the competition. So it's a modified version of the tutorial we have available on BrainDecode. In this modified version, I use the competition data. And I show you how you can fine-tune it on the task that was offered to the participants during the competition. So I'll stay a few seconds on this slide so that you can scan the QR code if you want the tutorials. And we'll dive in a few seconds. Okay, first tutorial, simple use case. We'll see how you can instantiate one of the BrainDecode models and then how you can train it on M&E epochs. So you've seen already how you can explore the BrainDecode documentation to find the model that you want. Then it's just a matter of importing that model. So here we use the shallow FBCSP net. It's one of the historic architecture, like one of the first deep learning architecture that was introduced for EEG signals, and it was with this architecture that the BrainDecode library was created originally. Then you can print the documentation of the model, so it's exactly what you would see, but less nicely formatted when you click on this model. Here you have the documentation, it's the same. But then, so instantiating the model is just like a few lines. So you have you specify the mandatory parameters, so number of channels, number of time points, number of outputs. And then if you print the model, you will see the list of every layer that is included in this model. And for each layer, you have the shape of the input that will receive, and then you have the shape of the output, and the number of parameters of this layer. So this layer doesn't have any parameter, but you see that the convolution here has most of the parameters, and then the normalization has a few parameters, etc. You have also the kernel size, depending on which model we're talking about. At the end of this description, you have the total number of parameters, the number of trainable parameters in case it's different. You have the size of the input that was passed to a model. you have the size in memory that was occupied for the forward and backward pass, and then you have the size of your model if you were to save the weights of this model. Then loading the data. So here we suppose that you have your own M&E epochs, but instead of using some real data, we'll create just an array containing some random data. So of course the classification will not work because it's just random data. And in the end we obtain some M&E epochs array. And we're ready for training. And so for training, a very convenient class that we have in BrainDecode is the EEG classifier. And so everything I'll say about the EEG classifier, we have the exact same for what we call the EEG regressor if it's a regression task. But so here for a classification task, in this EEG classifier, so while the original model, like the shallow FBCSP net, this is a PyTorch model. Here, when we instantiate the EEG classifier, this is what we call a scikit-learn estimator. And so this scikit-learn estimator has a fit method, which will train the model inside on the epochs, the data, and Y, the labels. And so this EEG, this scikit-learn estimator basically knows all the model names that we contain in BrainDecode. So you can simply pass the name of the model that you want to train. You could also pass the actual model, but it's much more convenient to pass the name of the model, because then you see that you don't even have to specify the mandatory parameters, such as the number of time points or the number of channel or the number of outputs, because this EEG classifier will automatically infer these mandatory parameters from the signal that you pass as input. And so, as I said, you just do net.fit, and you see that, never we passed the mandatory parameters. Like, the only way the EEG classifier is able to know the number of channel or number of time points is by looking at the data, because we have standards, like we know what the data is supposed to look like, and then it fits. And if you look afterwards at the fitted model, so the net.module contains the actual module, you see that it is the exact same architecture as before. And if you look at net.module.nchans for the number of channels, you see that the number of channels was indeed automatically inferred. So we have 3 channels, 1000 time points, 4 outputs, and the sampling frequency, the size of the window, and even the information about the channels, like their name, that was automatically found in the M&E epochs. Here you have a reference to the filterbank CSP net for the shallow FBCSP net. And in summary, if you have M&E epochs and you want to try a first approach using deep learning, you just pick one of the BrainDecode models and you just copy paste this line. So you instantiate an EEG classifier with the name of the model that you want to use, and that's it. And then you just call net.fit or net.predict, or all the scikit-learn functions will be compatible with this EEG classifier, and that's all you have to know to try a first deep learning approach with BrainDecode. Okay, now we'll have a look at the second tutorial. So again, a few seconds. If you need to scan the QR code, go ahead. Okay, second tutorial. How can you fine-tune a foundation model on EEG signals using BrainDecode? So before we dive in, a quick reminder about foundation models. In the broad sense, a foundation model is a model that has been trained on a large amount of data in such a way that they are easy to fine-tune for a new subject or even a new task, because they've seen a lot of diversity. They are very versatile and they are able to generalize to new types of recording. The end goal of using foundation models is to reduce calibration time, such a way that you don't need so much data from your new session or your new subject, because your model is already very generalized. And in the last 2 years, there has been a lot of attention, a lot of interest on foundation model for EEG signals. And so this is why I'll give you this tutorial on how you can use the models that are already out there and try them for yourself. So in the advanced tutorials of BrainDecode, we have this tutorial that is using a motor imagery dataset. But for this workshop, I duplicated the tutorial and slightly modified it in such a way that now it uses data from the competition. So you have the notebook on Google Colab. And so it will show you basically how any participant could have reused the foundation model to train on the first challenge of the EEG 25 competition. So first thing we have a few imports. But then first important thing we load the data. So here we have the EEG challenge dataset, which is a class defined in EEG dash. And you don't even have to download the data before that. So this EEG challenge dataset class will automatically look if the data has been downloaded or not. And if not, it will download it. Then what we do, we set the montage of the electrode. So this was the montage that was used to record the data. And by setting this montage, the recordings will have the channel locations associated to each channel. Then we set a few dataset parameters, so the sampling frequency or the information about some channels. So we see that the sampling frequency is 100 Hertz and we have 129 channels. Then we have some preprocessing. So this preprocessing is exactly the same as what we provided in the start kit for the participants to the EEG challenge. Basically what it does is that it adds a few information in the metadata, and then we are creating the windows based on the events present in the data. But here is the important part. So on that point, so we have the Windows dataset. It's a dataset from BrainDecode that contains epochs that we will be able to use for training. I won't go too much into the details, but basically this is exactly what the participants of the challenge were using, and this is on a very similar type of dataset that they were evaluated. But so now, when you want to use a foundation model, what do you need to know? The first thing you need to know, and first thing you need to do, is to find some pre-trained weights. So here we'll use the signal JPA weights that are available on Hugging Face. And so you see on Hugging Face, you have a model card with a picture of the architecture. You have a small description on how you can reuse those weights, like a minimal example. And then you have the files that contain the actual weights. And basically, in this PyTorch function, the torch.hub.load state from URL, what will happen is that this PyTorch function will download the weights from this path. So these weights correspond to what you have here. It will first download the weights and then load them into memory. So you will have a state dic in memory, a dictionary containing a mapping between the name of the parameters to the actual weight matrix. Then the second thing you need to know is to instantiate the corresponding architecture. So here it's the pre-local downstream architecture of the signal JEPA model. You specify here the signal-related parameters and the number of outputs, so just one here because it's a regression task. And then you load the weights into the model. So to load the weights into the model, you basically just need one function, which is the load state dic function. The rest around is just for sanity check. We check that we have exactly the keys that we expect, not more, not less. And then you're ready to fine-tune your model. It's as simple as that, basically. So here you have basically two options for fine-tuning the model. Either you can fine-tune all the layers of your model, so the pre-trained ones, plus the classification layers that were added to turn this model into a model that can give you like either class or regression score. Or you can fine-tune only the new layers, only the new classification or new regression layers. And so fine-tuning all the layers is pretty straightforward. You just train your model for a few epochs, that's it. But so here we'll see how we can train only the new layers. And to do that, basically you need to freeze all the layers that were already pre-trained. So how do we do that? We'll iterate over the layers and we'll set the require grad equal to false on all the layers that we do not want to train. So here we have a list of new layers. And so if it's not within these new layers, we set the require grad equal false. And then again, for sanity check, we can print which layers are trainable and which ones are not. And finally, so in the previous tutorial, you've seen the EEG classifier. And here you have now the EEG regressor class. So it's the same, except that the loss function is a regression loss, and the metrics are also a bit different. They are regression metrics. But so here, what you can do, so you probably remember before we were instantiating this EEG classifier with the name of the architecture, but here we directly instantiate it with the actual model, the model that was instantiated here, so the SJPA architecture. And then, as before, you can just do classifier.fit with the dataset and the labels Y. And we just trained for 10 epochs for this example because we want something short just to check. And now in this example, as we have some real data, we can see that the loss is decreasing, that the mean square error, so it's the negative root mean square error, so it is increasing. Also, like there's a minus before, but anyway, so ignoring the minus, we see that the error is decreasing. We go from 1.5 to 0.8. And the same goes with the validation loss. The validation loss decreases and the validation root mean square error is also decreasing. But you can do even better, even nicer and more satisfying. You can use what are called callbacks to do the weights loading and freezing the layers. So these callbacks are subtleties of the EEG regressor. But basically, here we will define two callbacks. So one that is already pre-existing to freeze the layers, and then one that we are creating here to load the weights. And so here you can see the details of the weights loader. It just has a method that is straightforward to understand on train begin that will be called when the training is beginning, and that will take the neural network regressor and load the weights in the module. And now, basically what we can do is go back to the nice implementation that we've seen before and only call the architecture by its name. We don't have to provide any signal-related parameters because they will be automatically inferred by the EEG regressor. You have two callbacks that are added, the weights loader and the weights freezer. And we provide the URL to the weights loader. And then we call just classifier.feed the same way as before. And we see that the loss is decreasing again. And same goes for the validation loss. So I hope this helped you understand how you can do fine-tuning on a neural network with BrainDecode on EEG data. And I wish you a good continuation for the end of the workshop. Bye.